here today, and then I have a couple of little problems as well to wrap up the chapter 2 information. Anything you may have thought of? Did you get an email from Cody yesterday? I guess not. Good. I actually forgot to type it down here about the scale activity, extra credit opportunity for the class. So there is, if you didn't see that, make sure to hunt your emails. If you can't find it, zap me an email. I can send it on to Cody. He can send it again. In that email is a code that's unique to you. So you can't use your friend's code, otherwise they're going to get the credit. So that's why you need the email. And there's a website. When you click on you go to the website, you put the code in. That way the system knows who you are, and you complete the activity, which is described rather thoroughly in the email. You'll get 5 points extra credit for completing that. It closes next Tuesday. So I just wanted to make a verbal announcement, just in case you aren't accustomed to looking at your emails a lot. Anything you may have thought of before we continue? All right, let me actually write myself down so I can put it in the upload, because I forgot to type it down there. All right. We were talking about monoatomic, I can't wait for that projector to get fixed, monoatomic ions last time, and we left off at the bottom of number 8, which basically we were talking about the trend. Remember, this periodic table on the screen does not show you all your ions. The ones that you'll be responsible for knowing are the ones that are what we call constant charge, meaning the element only makes one type of ion. For the vast majority of the representative elements, meaning not transition metals, that is going by the group number. Tin and lead make more than one type of ion. Therefore, you don't need to memorize that tin and lead make +2 and +4. It's only the ones that make one type of ion. There are 3 in the transition metal area that do make only one type of ion. Therefore, you'll need to know them, and that's what the little table in number 9 is all about. So, they're wanting you to fill it in. The most important thing, I think, is the last column. You need to know that silver is +1, Ag plus, nitrogen is +1, cadmium is +2, and zinc is +2. What major class of elements makes cations? Metals or non-metals? Metals. So in general, when you're looking at a chemical formula, if you see a metal there, more than likely it's an ionic compound, because more likely that's an ion. I have to say more than likely because we do have some polyatomic anions that have metals in them. We also have a polyatomic ion that doesn't have a metal, but it is a cation. So generally form cations is metals. And the major class of elements that tends to form anions, therefore, is nonmetals. In order to consolidate what you need to know, hopefully you've already found it on Canvas, in the handouts module, I have created about 10 years ago a need-to-know ion sheet. The first page is the monoatomic. And all of them go by the group number except zinc with a little asterisk behind it, silver ion, and cadmium ion. I have inserted those 3 as well into this, so you just have one source. This is the list. Any questions before we go to polyatomics? Sort of nice to get to that point, but it's Friday, but we're pushing the time. We want to make sure we get things done right. All right, so now we're going to go polyatomic. Poly, more than one atom is there. We can see that in our sulfate with 2 different representations, and in our ammonium cation, which is that one cation just referenced that doesn't have a metal in it. I know that on page 55 you do have a table there, but there's also several tables in your textbook, which I know can be confusing. Therefore, to consolidate into one source material, the second page of the need-to-know ion sheet has the need-to-know polyatomics. So I would strongly suggest either downloading it and using it electronically or printing it out. Either way, electronic highlighter versus real highlighter, highlight the ones you know in one color and highlight the ones you don't know in another color. Don't cross off the ones you know, because you still do need to keep looking at them so you don't forget them. Are we good? In 13, we have a definition for ionic compounds, and our textbook is not very clear on that definition because it says formed from cations and anions, which is not very helpful. So that's the textbook definition. In order to make sure we're understanding ionic compounds a little more, I'm actually including a slide that you don't have lecture activity question 4. We want to make sure that we understand how ionic compounds exist, and that helps us understand why we rate the formulas in a certain way. So they exist as a lattice of oppositely charged ions. Notice it's going orange, silver, orange. We don't want same charges next to each other. That would repel, opposites attract. So I have two different representations at the bottom of the screen. And if we're going to write a formula, let's say this is sodium chloride, we can't actually know exactly how many sodium cations or chloride anions are there. And different size crystals of salt would have different numbers. Therefore, we always reduce the formula for an ionic compound down to the lowest ratios. And I'm hopefully helping you understand why. Because a sodium chloride crystal or any ionic compound crystal would never have the exact same number of ions as another crystal. And therefore, we can't write a formula that gives the exact numbers. Whereas we can do that, I see the hand one sec. I just want to finish the sentence. We can do that for molecular compounds. Yes?
So in our lab for this week, we were doing that thing where we were trying to figure out how many atoms thick our aluminum foil is. You can't do that with ionic compounds?
Well, we can, but there could also be different thicknesses of aluminum foil, just like there could be different sizes of crystal lattices. Meaning, if you're writing a formula for an ionic compound, including the exact numbers, every sample would have a different formula. If that doesn't make sense. See what I'm saying? Okay? It'd be different if all the crystals are always the same size, but they're not. In a molecular formula, say octane, it's always the same size. It always has the same numbers. All right? Make sense?
Mm-hmm.
Okay. So I found over the years this slide helps students understand why we always reduce, because they exist in these lattices, which could, of course, be all different sizes. As far as to expand upon the textbook definition of formed from cations and anions, and this goes with 13a, of course, we must contain ions and not molecular compounds, therefore you need to be able to recognize that there are ions present, which is why we need to know our ions. They also need to be electrically neutral. They are compounds. They're compounds. They're no longer ions once you have the opposite ion there. Therefore, we need to make sure that the total positive charge equals the total negative charge. If it doesn't, then it's not a compound. It's an ion. They contain cations and anions. Of course, this is how we identify the compound as being ionic. It is, I can't even say traditional, it's just a rule that the cation is always written first, which is why we say sodium chloride, not chloride sodium. Polycompounds are kept grouped together as a single unit because it is that unit that is the ion. Meaning we might at times have to use parentheses in order to have multiple polyatomics. And the extra I wrote, you don't have really a bullet point for. We always write the lowest ratio of cation to anion as the ionic formula. We just talked about it, but I wanted to have it all in one place. Again, you need to know your ions to be able to recognize something as ionic, which if you watch the video, you see that there's a different naming system in something ionic versus molecular. Questions? Which representation of an ion is more useful for writing the formula of an ionic compound? A symbolic or particulate? Meaning, does that help you write a formula? You don't know what elements are present. You just know there's two different elements, one atom each, right? Of course, if we had Na plus and Cl minus, that is much more useful for writing the formula because we can put them together and get our NaCl. We're switching representations, and often when that happens throughout the semester, we'll have a couple questions to remind ourselves as to why we're using certain representations at certain times. Is it correct to say a molecule of AgCl? For one thing, we usually don't call ionic compounds molecules, although they are still molecular. But there's many units there, right? It wouldn't be correct to say I have one of these. In other words, the singular is really what's more incorrect than anything. Remember, we're reducing. You don't know the exact numbers you have. So we have many silver chloride units. It's written as silver chloride referring to the number 15 because it's reduced. Any questions before we go to the next section? letters and sometimes numbers, such as C8H18. So we're using letters and numbers to represent our formula. From our textbook, the definition is typed out here, number 16. Chemical formulas are used to express the composition of molecules and ionic compounds in terms of chemical symbols. Is this a chemical formula? Yes. Is there something more there than just chemical symbols, meaning elemental symbols? The textbook definition leaves out the idea of the numbers, and I think the author thought, well, yeah, they know that. Well, we've had students in the past that got confused by an incomplete definition. So it says what is missing from the definition is shown in the formula for octane, and are only symbols shown? No, we have numbers too. And that might be like, duh, to you, but somebody might be like, oh, okay, that makes sense now. Definitions sometimes get to be incomplete because authors just make assumptions. We're going to now make sure we know the difference between a molecular formula and an empirical formula. Molecular formula, as defined in number 17, shows the exact number of atoms of each element in the smallest unit of the substance or the molecule, meaning C8H18 is octane, and there are exactly 8 carbons and exactly 18 hydrogens. An empirical formula is reduced. Tells us which elements are present in the simplest whole number ratio of their atoms. Meaning, if I wanted to reduce this, the simplest ratio, that would be C4H9. The C8H18 is the molecular formula, which we will use for my shorthand, which you might see on quiz keys and whatnot. And the C4H9 is the empirical formula. Empirical formula is not telling us the exact number, just like NaCl does not tell us the exact numbers. Any questions? I did put number 18 on the lecture activity list, but I also have those molecules in color on the screen. There is a color coding system that is traditionally used, and I want to actually give you a couple of those. So blue is often, almost exclusively used for nitrogen. Red, oxygen. Sorry, I'm abbreviating blue with red. White, hydrogen. You could either have black, and that's what I want to abbreviate, or gray, for carbon. Or I'm forgetting yellow. Oh, getting a little there. Sulfur. And green, fluorine. Meaning if you're looking at your textbook and they're showing you images like that on the screen, you can kind of decipher what's there. But it's most important for number 18. You can't really complete the problem if you don't have the color versions, you don't know what atoms are there, or what elements are present. So now you can kind of maybe make a note in 18, or if you wrote down a little coding system, and that way you'll be able to complete the problem if you desire. Any questions? Another definition we have on number 19, page 57, is allotrope. We've actually looked at some allotropes already. These are one of 2 or more distinct forms of an element. When we did the diatomic versus polyatomic table, and for our diatomic element, I used the example O2, and for the polyatomic element, I used the example of O3. Those are allotropes. Those are 2 different forms of oxygen. Many students also know about carbon allotropes. Might not put the term to it at the time. Graphite, this is diamond. There's also a bunch more. A real cool one is buckyball. It's a particle level size soccer ball basically made out of carbon atoms. It's my favorite one. But that's the idea of graphite and diamond both being forms of carbon. It's the same idea as diatomic oxygen and ozone being 2 forms of oxygen. Yes?
Would an allotrope also be H2O versus H2O2?
No, those are 2 different molecular compounds.
It has to be specifically on an element.
It's really at the elemental level. I put 20 and 21 on the lecture activity list. Again, you're looking at different representations to help you understand what information we can get from different representations. And maybe why we're making that switch. And the rest of this chapter, chapter 3, and getting into chapter 4, that also making that switch for a why. So there are a lot of personal answers in number 21, so if you want to look at the answers, I might just write student-driven or personal answer for some of those. Have you thought of anything? Any hands? I'm putting that back up because if you look at page 58, right, babe? Our ion formula also here before the why not? Yes, they are, because we're given the lowest ratio of ions we're reducing. And then you can see there's number 23 there that fills up the rest of the page. And if you took a picture of it or have a photographic memory, that was also on the list for lecture activity problems. But let's do a roll of this, just so we can get a little practice in it as well. So I like doing a roll on the second table, and let's see which one I want to do today. Let's do the calcium row, the second row in that second table. So to know what ions we're using, what would be the charge on the calcium ion? +2, I heard? Is it group 2? Or 2 plus, doesn't matter anyway. Does anybody know the formula for nitrate? I know 3, what's the charge? -1, I heard? What about sulfate? Very good. That's the one we have on the screen a couple times. Phosphate, anybody? PO4 3 minus. And hydroxide. OH minus. Good job. I heard that on more than one mouth, sorry. So we're going to combine those different anions with our cation, making sure that we're electrically neutral. Positive charge equals the negative charge. We're going to make sure we write our cation first. We're going to keep our polyatomic group together. And if needed, we're going to make sure to reduce. So how many nitrates will I have to cancel out the charge on the calcium? 2. I have 2 back in the back. So you have to put 2 nitrates. That's why I need my grouping that polyatomic, so that NO3 stays together. Notice there are no charges written in the formula because there is no charge now. We've canceled out the charge. How many calciums will I need to cancel out the charge on the sulfate? 1. They both have the same magnitude of charge. It's a 1-to-1 ratio, and I didn't spread these guys out enough, so I'm just going to drop that down a little bit so we don't get all askew. So that's just going to be CaSO4. I do know that some students like to parenthesize their polyatomics no matter what, and it would technically be marked wrong with parentheses around that sulfate. It's just generally not done if you only have one of them. It's a common student question, so I just wanted to address it right away. If you put parentheses on it, it's not like it's going to be wrong. If you do it in Moodle, it might give you the red box again. How many calciums and phosphates will I need to get a neutral calcium phosphate compound?
3.
How many calciums? 3. How many phosphates? 2. Many have learned that those numbers kind of tell you something. So if we cross the charges in a way, meaning you can write this. The phosphate had a 3 on it, so I dropped that 3 over here. The calcium had a 2 on it. Oh, I'm going to have to parenthesize, and that got really messy now, so I'll write it again. And have 2 of that. Ca3, PO4, 2. Or you can use logic. If I have 3 of these, I'll have a +6 charge. If I have 2 of those, I'll have a -6 charge. And that will cancel out. When you're doing the crossing those numbers method, make sure to check that you don't need to reduce. Also, I'm going to do an example which isn't here. I'll just pick it up on my head in a minute. How many hydroxides will I need? 2. Each one's 1 minus, my calcium's 2 plus. So I'll need 2 hydroxides. Good. Let's combine a tin-4 ion, Sn plus 4 with oxide, O2 minus. Hopefully, it makes sense that, if I want to have a neutral compound in the end, I need 2 oxygens. would give us the correct answer of SnO2. If you want to do the crossing the numbers idea, meaning writing the Sn and the O, putting the 2 from the oxygen by the tin, putting the 4 from the tin by the oxygen, and don't look at the numbers, you don't have the right answer. Then you have to need to reduce. So one way to do it, but one way might lead to an extra step of just checking to make sure that you don't need to reduce. 2 fourths, reduce to 1/2, so we'd have to reduce to get the same answer. Question?
When is it like, when should you reduce and when should you just leave it? How do you?
If you're doing ionic compounds, you always reduce. We always use the lowest whole number ratio. It's just often we get that lowest whole number ratio right away, right? Anybody else? So depending on how much practice you need, we have those 2 big tables. All the answers are on Canvas. You good? If you go to page 59, remember that hopefully on my TAs are doing this nomenclature discussion. I know some of Amanda's students she said very enthusiastic about it, which is great. You're good at practicing some nomenclature discussion. There, of course, is the Chapter 2 PowerPoint. There's a handout, actually not handouts, handout on Canvas. I'll have to fix that to singular. You will be having to name ionic compounds, which could include transition metal compounds. We need a Roman numeral if it's a transition metal that is a variable charge cation. We, of course, will have zinc, silver, cadmium showing up as you need to know those, but tin and lead have more than one charge, so there'll be a Roman numeral as well. Polyatomic ions will be included. As far as our molecular compounds, compounds containing hydrogen are a little different than others. There are some common names as well. We expect you to know what water is, H2O, instead of saying dihydrogen monoxide all the time. Acids is what I'm going to focus on in lecture today. So we have 2 different types of acids, binary and oxo acids, and if you've watched the video, you should actually be able to fill in the rest of page 59. I'm going the wrong way. All of 60 and, all of 60 and maybe at the very top of 61. We're going to be picking up on number 31, page 61. I'm actually going to get a brand new sheet out too. I don't have any PowerPoint slides for this because sometimes I don't have time to do it. So, number 31 is our definition for acids, defined as a substance that yields hydrogen ions when dissolved in water. We'll have more definitions for an acid in chapter 4. But for right now, you can see acid basically being, you're going to have H plus an anion. Depending on the charge of that anion, if it's only -1, then you'll need 1 H plus. Or if it was -2, then you need 2 H plus. So you need enough hydrogen cations to cancel out the charge on that anion. And depending on the type of anion, we have 2 different naming systems. Let's just first do 32 to make sure we know how many hydrogens we need. So for the first one, top row, left-hand side, with the sulfate, SO4 2-, how many hydrogens will I need? Or H pluses, sorry. 2. It's 2 minus, we need 2 of them, so you end up getting H2SO4. For the second one, contain oxygen, and therefore they're called oxoacids. Meaning H plus oxoanion. Which is just a polyatomic anion that contains oxygen. We're going to think about the binary acids first. Number 33 was placed to your right for binary acids, H plus monatomic ion, or two elements present. And we have a process in 34, and then we have an example, and then we have another example. So for our binary acids process, the first part of the process is hydro. Hydro is always present for binary acids. If you see the prefix hydro in the name of an acid, it is telling you that it's binary. Then to that you add the element name with the ending changed. Wow, that got a little wonky. Well, how do we change it? We add the suffix "ic." And of course, we always have the word acid at that. That's why we have acid kind of typed over in the side. So for our example, HCl, since it's binary, hydrogen and chlorine, the only two elements present, we always have that prefix hydro. We're going to add to that the element name with the changing ended to "ic," meaning hydrochloric acid. Does anybody know the name of the other example, HBr? Hydrobromic acid. That's the HCl here. Any questions? We do have more practice on the next page after we get done with our oxoanions. But if you have a binary that you name it, always start with hydro. If you're seeing the name and hydro's there, it's telling you it's a binary. For our oxoacids, it's extremely important that we actually know the name of the anion that we're using. So I'm going to shove up a little bit. So again, 35, you probably wrote it in the page, but oxoacid is an H plus an oxoanion with the polyatomic containing oxygen. Note that the process depends on the ending of the name of your anion. So name of the anion is where we're starting for our name of the acid. Depending on the ending, if it's ITE, we change that ITE to OUS. So we're changing the suffix. If the ending is 8, that changes to "ic," and then of course the word acid. So what's the name of the Depends on the number of oxygens. So our chlorine sequence, we have, the first one is HClO4, and then we can go down to actually, I just went to the anions. ClO4 minus, then we have ClO3 minus, ClO2 minus, and ClO minus. For the ones with more oxygens, it's 8. For the ones with fewer oxygens, it's 8. But to distinguish these two, there's a different prefix used. This is perchlorate. We remove an oxygen, we keep the 8, we remove the per, so we have chlorate, which is why Br3 minus was the bromate. If we remove another oxygen, we have to change the suffix because we've already lost the prefix. This is chlorite. And another oxygen, we can't really remove that ite, so we add the hypo. So if you know the 8 version without the prefix, if the oxygen is added, you add per. If the oxygen is removed, you change the 8 to ite. Okay? If you remove another oxygen, you keep the ite, you add the hypo. Not all ions have a 4 in the sequence, such as sulfate and sulfite. But sulfate is SO4 2 minus, and sulfite is SO3 2 minus. There was no prefix to take off, I had to change the 8 to an ite. So you can limit your list to the 8s, and then just know what happens when you remove an oxygen or an atom. Very common question, that's why I was like hunting for hands. Yes? I see two, sorry.
Yeah, so for the bromic acid, are we not including the hypo then?
Hypo only goes on binary.
Binary, okay, and that's an octic
Oxo
acid.
acid. The oxo acid, we start, or excuse me, we start with the name of the anion.
Okay, so then for the hypochlorous,
Yeah.
we did keep the hypo?
Hypo is part of the name of the anion. The anion is named hypochlorite. So you start with the name of the anion with the suffix. So you might have a prefix there from the anion. Like our perchlorate. Well, HCl4 is perchloric acid. The name of the ClO4 minus is perchlorate. We write down the name of that anion. Since this is an 8, we change that to it. So perchloric acid. So you might still see prefixes, but there won't be hypo. I'm sorry, hypo is the ClO minus. The hydro always tells you binary. Any others? Sorry, I didn't see it over there. I'm trying to stand. It does take practice. Once you get the hang of it, it's not that hard. Let's do practice number 37. Just shove this up so I have my clean paper here. So we have carbonate, CO3 2 minus. First off, hopefully you see we need 2 hydrogens on that. So from our CO3 2 minus, we add 2 hydrogens to get a neutral compound, H2CO3. Anybody know the name of CO3 2 minus? Carbonate. So we're changing H to an it. So this is carbonic acid. This right here is carbonate. From the other page, for S2 minus, which is sulfide, we had to add 2 hydrogens. We already did that. Well, it is binary, therefore we're going to have hydro. Name of the element with the ending change to add it. Hydrosulfuric acid. And we actually just already did the last one by accident. So the perchloric acid goes for the third one there with the perchlorate anion. One last little thing we need to do is the hydrates. Hydrates are compounds that have a specific number of water molecules attached to them. They are ionic compounds with a number of waters per formula unit of the compound, such as BaCl2 concepts are within the reading, also they stop if there's a question. Homework problems are at the end of the chapter. We good? That's the end of chapter 2. I have to put that up there while we're doing the practice. Sorry. Forgot that's why I'm there. Meaning we're going to look at chapter 3 for the next 9-ish minutes. Chapter 3 is titled Stoichiometry, but there's a lot there besides just stoichiometry. It is a hefty beast of a chapter, and exam material will be 3.6. You usually get there. We still have 9 minutes today. We have a little extra on Friday. We have Monday and Wednesday as well. Some of which I'm hoping is review of this, but atomic mass, we then reorganize. Notice 3.4 is right after 3.1. We do that, and then we look at Avogadro's number and molar mass of an element. Then we look at molecular mass, along with molar mass of compounds. Percent composition, experimental elimination of empirical formulas is one that you might know one method, but I don't think you know the other method. That I think would be new for everybody. Then after exam material, but possibly taught before the exam, is chemical reactions and chemical equations. No, we don't reteach hot balance. We briefly do a couple practice. Then we have the stoichiometry coming into play. Amounts of reactants and products is traditional stoichiometry, but then of course we added limiting reactants. And then finally, reaction yield, like percent yield. You may have heard that term before, to round out that chapter. Any questions before we jump in? So, look, what page are we on? We're on page 66. What particles contribute to the mass of an atom? Remember, we have protons, neutrons, and electrons, but relatively, electrons are so small in mass that we really don't count them. So, to determine the mass of an atom, we're looking at protons plus neutrons. Now that's why the mass number, or the atomic mass, A, in your nuclear symbol, was just counting the particles in the nucleus. The definition of atomic mass is now further explained, the mass of the atom in atomic mass units. Instead of just counting particles, now we're actually using a mass unit, which is the AMU. The AMU has been defined as exactly 1/12 the mass of a carbon-12 atom. How many particles are in the nucleus of the carbon-12 atom? 12, right? That's why the 12's there. Therefore, if we take 1/12 of that, we're counting each particle basically as an AMU. If you remember that table with the relative masses, we had the proton and the neutron each with 1 next to them. Now we're just putting a unit on that 1. Which means for the mass of a carbon-12 atom, in terms of AMU, since there are 12 particles there, it would be exactly 12 AMU. So carbon-12 has mass of 12 AMU. That is the exact number because we're really counting particles. It's also based on the definition of the AMU. What would this mean for the masses of other atoms? Well, fluorine-19 would be 19 AMU. Hydrogen-1 would be 1 AMU, 1 proton there, and helium, messy helium. Helium-4 would be 4 AMU. When we're looking at isotopically pure samples, it's a nice whole number. Any questions? However, when we look at the periodic table, we do not see whole numbers except for our atomic number. Why is the mass of carbon given as 12.01 and not 12? When we look at the periodic table, we're not looking at isotopically pure samples. We're looking at the samples of carbon in nature, meaning there are other isotopes present. Our atomic mass on the periodic table is an average of those other isotopes that are present, which is weighted by the percent abundance or how abundant each isotope is. So we can see in that little pie chart there that carbon-12 is the vast majority of carbon 13, a little slice of the pie, at 1.10%. Is there another isotope of carbon that you probably know about? Carbon-14 radioactive dating. It is so low in its abundance that even drawing the thinnest line would be over-exaggerating the amount of the carbon-14, which is why I believe the author left it off the table, but students have said, hey, what about carbon-14? What would this mean for a sample of 100 atoms of carbon? Of 100 atoms, about 99 of them would be carbon-12, and about 1 would be carbon-13, and you'd be really lucky to have a carbon-14 in your sample. Do you think the sample that was used to determine the data to produce the image was 100 atoms? No, that's why it's in percent. Of course, it was a macroscopic sample that was used. Next time, we'll continue at the top of page 67, although it's not the end of number 1, it is a nice break. We use the rest of number 1 to remind ourselves where we were.